Hello everyone. Today I will present our work called the tensor decomposition for compact network representation. My presentation has three parts. First, I will cover the basics of model compression, including its motivations, advantages, and challenges. Next, I will review the taxonomy of model compression approach, the background of tensor decomposition, and then present our work codec. The word codec stands for coupled tensor decomposition for compact network representation. And finally, I will share some experimental results and bring some demonstration. Let's start with the context. In recent years, deep neural networks have grown in both parameter and computational demands. In 2016, the largest model had fewer than 200 million parameters, but today, models can reach billions. For example, the GPT-4 model has around 2 trillion parameters, and more recently, the Grok 4 model even scaled to 5 trillion parameters. As the model continues to grow, they become costly and complex, leading to problems such as slow inference, expensive deployment, privacy concern, and environmental impact. Model compression offers a solution. Model compression brings advantages such as cost saving, reduced storage requirement, lower computational complexity. It allows on-device deployment with energy efficiency and faster inference, and also bring privacy preservation. However, compression model is challenging. We aim to reduce parameters and computational demands while preserving accuracy. This balance is tough due to information loss and model-specific optimization. There exist several model compression approaches. First, we have neural architectures, a method that automatically explores different designs to find faster and smaller models. We have quantization or factorization, where we represent the weight or the activation with fewer bits. For example, instead of using the full 32 bit to represent the parameter, we can use 8 bit to represent them to save memory and computation. We have pruning or specification, which remove redundant or unimportant element in the network. With pruning, we have two types. Unstructured pruning, removing parameter in the model without any specific patterns. And secondly, we have structured pruning, which remove kernel, filter, or even the whole layer in the model. Next, we have low-rank approximation, consisting of matrix factorization and tensor decomposition. This kind of method breaks the original tensor into smaller factor matrices or core tensors. With compact model design, we replace the standard operation with more efficient operation. For example, in CNN, we replace the classical convolution operation with group convolution. Or in transformer, we replace the multi-head attention with multi-query group attention. Finally, we have a knowledge distillation, in which the larger model transfers the knowledge into a smaller model. We call them the teacher and the student models. And the student model will try to mimic the behavior of the teacher model during training through backpropagation. In this work, we focus on low-rank approximation, specifically tensor decomposition. To understand our method, let's review a few concepts. A tensor is a generalization of vector or matrix in a multidimensional array. For example, a vector is a first-order tensor, a matrix is a second-order tensor, and so forth. We have third-order tensor and fourth, fifth, sixth-order tensor. Rank 1 decomposition express a tensor as the outer products of vectors. In the case of a matrix, it is expressed as the outer product of two vectors, while for the case of a tensor, it is expressed as the product of three vectors. What about the case of a higher rank? This idea naturally leads to the definition of canonical polyadic decomposition, CPD. The CPD express a tensor as the sum of several rank 1 tensor. In equation 3, the original tensor is expressed as the sum of R rank 1 tensor, and R is called the canonical rank. It is the minimum integer that ensures the equality in equation 3. Or we can rewrite equation 3 more compactly as shown in equation 4. The tensor T is expressed as the CPD of three-factor matrix A, B, and C. And importantly, the CPD offers a compact representation that reduces the number of parameters of the original tensor from cubic to bilinear. So far, we have considered the case of a single tensor, but an important question arises. What if we have multiple tensors? Is there a more effective way to decompose them? Yes, the answer is the couplet CPD. Let's consider a set of tensors of same size. For example, in this case, T1, T2, T3 with the same dimension. For the first approach, we can decompose each tensor separately. For example, T1 will be expressed as A1, B1, C1, T2 with A2, B2, C2, and so on. For the second approach, we can jointly decompose them in a chosen mode. For example, in this case, we consider the mode 1, the mode of the factor matrix A, because recently and oftenly in CNN model, the first mode often occupies the largest portion of parameter. And if we compare the two methods, clearly the second method, the couplet CPD, offers a more compact representation to decompose the original tensor, because the number of parameters for the first approach, we need n tensor. We need n matrix A, n matrix B, and n matrix C. While for the second approach, we need only one matrix A. So clearly, it's more efficient. The algorithm to compute the separate CPD was presented in the well-known paper by Konda on tensor decomposition. But how do we adapt this idea to compute the couplet CPD? In this work, we use the alternating least square approach, ALS. The objective is to decompose the tensor, the original tensor Tn, into the vector matrix A, Bn, and Cn, while minimizing the reconstruction error, the Frobenius norm of the differences between the original tensor and the reconstructed tensor. The ALS approach will fix A and Cn to solve for Bn fix A and Bn to zone for Cn, and then fix Bn and Cn to zone for A. And this procedure will be repeated until a conversion criterion is satisfied. For example, the conversion criterion can be the number of iterations or a threshold of the reconstruction error. Each subproblem fix An and Cn zone for Bn, for example, with all but one matrix fixed reduced to a linearly square problem. The solution for this problem can be found in our paper. Okay, that's about Lorentz approximation definition. Now let's consider a convolutional neural network. This picture is a simplified illustration of a CNN model with 4 layers. Of course, in CNN, we also have a fully connected layer, normalization layer, and activation function. However, in our work, we focus on CNN layer only because they occupy most of the parameter of the models. We apply the complexity parallelly on convolutional layer of the model. But to clarify, let us focus on the case of a single layer. In a single CNN layer, we have multiple filters. For example, we have 8 filters from W1 to W8. Our approach codec is designed to tackle the redundancy among filters of the models. It contains a two-step. First, we will classify the filter into different groups so that filters in each group share stronger similarity than others in different groups. After obtaining the group or the cluster of filters, we will apply the coupled CPD to factorize them into smaller factor matrices A, B, and C. One question is that why do we need clustering? Our intuition is simple. Because let's consider the case if we do not apply clustering, we will have 3 clusters in this case, cluster 1, cluster 2, and cluster 3. And we can observe that in this case, cluster 1 and cluster 3 is not well classified because, for example, in cluster 1, filter 2 and filter 3 do not share similarity in the first mode, the mode of matrix A. If we apply the clustering, all the cluster will be well classified as shown in this part of the figure. Okay, that's about why do we need clustering. And now we consider the question, how do we cluster the filters? Let's consider 2 filters. In this work, we choose the k-mean clustering algorithm because it is simple and effective. And let me recall that in the k-mean algorithm, we need to calculate the distance, the pairwise distance between filters so that we can group them into different clusters. So if we consider 2 filters, WE and WG, to calculate the distance or the similarity between them, of course, it is equal to the distance of the unfolding matrix. And we need to remember that in our framework, we aim to group the filter that are similar in the subspace of the first mode matrix, the matrix A. So instead of calculating the distance between the whole pointer WE and WG, what we concern is to compute the distance between the vector matrix AE and AG, and to obtain the distance between the vector matrix, we need to perform the CPDs of each filter. For example, equation 7 and equation 8. So the CPD of the two filter WE and WG, we can obtain AE and AG. However, even in the case we have the CPD representation, we still have problem with the ambiguity. So, but at the same time, the truncated SPD singular value decomposition of the unfolding matrix WE and WG, with SPD we obtain the left and the right singular vector matrix U and V, and sigma is the diagonal matrix of singular value. We observe that AE and UG span the same range space if and only if their orthogonal projectors are identical. Based on this observation, we propose to measure the distance between AE and AG using the distance between UE and UG and expressed as the projected distance between them. For example, in equation 11, we calculate the distance between UE and UG by the Frobenius norm of the differences between UE multiplied with its pseudo-inverse matrix and UG with its pseudo-inverse matrix. Okay, now we have solved the problem of clustering. And now let's move on the second phase of our approach, the coupled CPD. How do we perform the coupled CPD? The answer is simple. We perform the coupled CPD parallelly on each cluster using the AOS approach that we already covered in previous slide. Okay, now let's take a review on the overall process of our approach with two-step clustering and coupled CPD. Through our approach, now if we forget about all the detailed steps, the clustering and the coupled CPD, we see that from the original layer with separate filters, we have jointly decomposed them into vector matrix, and the forward is already solved with clustering and coupled CPD as you have already seen it. But now after obtaining the vector matrix, we will use them to replace the original filters. But how do we perform this replacement? This leads to the codec-based convolution decomposition. In CNN, the original filters is convolved with the input data E to generate the corresponding output feature map OE. By applying the coupled CPD, we factorize WE into A, BE, and CE, substituting equation 13 to equation 12 leads to equation 14, and we observe that equation 14 involves a sequential element-wise multiplication between the input E and the vector matrix A, B, E, and CE. And more detailedly, we can perform the equation 14 as below. First, we use the input E to multiply with the matrix A to obtain the output X, and then we use X to multiply with BE to generate EE, and EE with CE, we have ZE, and finally, we need to perform a summation over the dimension of the range to obtain the ultimate output feature map OE. And the implementation of the equation leads to the codec block. From the original classical convolution layer, we decompose it into factor matrix, and then we use the factor matrix to create novel operation, including one-point wide convolution and two-depth wide convolution. And this block, the codec block, can be easily implemented in deep learning frameworks such as Python or TensorFlow. And we need to note that by choosing the appropriate rank and number of a cluster K, we can control the compression level. And the condition for a positive compression is that the number of parameters of the original convolution must be larger than the number of parameters of the codec block. Okay, that's all about our methodology. Now let's move on the experimental result. We apply our method on several CNN architecture and datasets, but now I will focus on one representative result, the case of the ResNet 50 model on the ImageNet dataset. We measure the performance with the top one accuracy and the acceleration with the reduction on number of parameters and number of computation max. We also compare our method with different compression approach such as running neural architectures, distillation, and other decomposition approach. For example, in this case, we compare codec with the Tucker decomposition, and we observe an improvement in accuracy with around 10% of more reduction on number of parameters and computation. When we increase the compression level, our method is able to bring a 3 times smaller and 3 times faster model. Beyond this quantitative result, we also bring qualitative result. Specifically, we use GradCam gradient class activation map method, in which allow us to observe that which feature that the model have used to make the prediction. This one, for example, in this case, with the input image, we have infer on the original model with 0% of compress, and we can see that the model focus on the wings and the head, important feature to recognize that this is a butterfly, and with 3 level of compression, 40, 60, 80, we observe that the models are able to preserve important feature of the object on the wing and the head of the butterfly. And we also observe similar phenomenon with other classes, a whale in this case, or ball players in the third case. We also apply our approach to downstream tasks such as object detection, instance segmentation, and key point detection. For example, in this case, we apply codec to the faster RCNN model. We measure the performance through the mean average precision and the compression through the inference speed with number of frames per second, the runtime memory, and the require storage size. We can see that our model is able to double the number of frames per second with a small loss of accuracy. Here's the result for the human key point detection task. Similarly, our compressed model requires less storage requirement with faster inference speed. Here's some related work on Lorentz approximation, and the code for our work is available on the homepage. Please give a check. Thank you for listening.